Here we are looking at something called successive ionization energy, and we're going to also make some connections with photoelectron spectroscopy. So right here we've got a data table, once again, successive values of ionization energy for the elements. So what's important is to remember what ionization energy means, and ionization energy is the energy required to remove a valence electron from a neutral atom. We can be a little bit more specific there if or when we wanted, talking about gaseous atoms and all of that, but it's just that energy to remove a, but more importantly, we could say the first electron from a neutral atom. The difference is we're talking about other ionization energies, and these guys right across here. I1 is the first ionization energy. I2, 3, 4, 5, 6, and 7 is just the energy still to ionize it, but to keep taking electrons. So the second is the energy required to remove the second electron. Valence, in some cases, I'm just going to keep it as electron from an atom that has already lost its first electron. I put valence on there, but I took it off because sometimes if we only have one in that valence shell, this next one isn't going to be a valence electron. So we're just talking about removing the first electron. Then after we've done that, taking the second one, taking the third one, taking the fourth, taking the fifth, taking the sixth, and taking the seventh. I'm not on all of these going to type my answers in because that's not as efficient as I pop down to the bottom there, seeing that we do have the filled in version. So I am just going to be talking through these next two definitions. It asks the pattern of first ionization energies from left to right on the periodic table. And this is here only to remind us that we learned this already. Ionization energy goes up, 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 up as we go across the table. And when we look at the details here, we'll see that not everything increases precisely a certain amount from the before one. And even we'll see not everything increases, but we start at about 500, we go to 1500, and it increases. That's because as I go left to right, I have more Zeph, I have more attraction, and it becomes harder to take that electron. But the other pattern we want to see here is first to second. So we defined those. Taking the first electron is 500, 700, 1000, 1500. But all of these are higher. We notice that taking the second electron from any of them is higher than taking the first electron for all of them except for argon. And why would that be? Right here, after we've already lost our first electron, we've got the pattern there. We now have the same number of protons pulling on fewer electrons. By pulling on and being attracted to fewer electrons, each of those electrons feels more attraction, feels more Zeph, feels more inward pull, and is pulled a little bit closer. So that next electron, taking away a second electron, is always harder than taking the first because it has more attraction. Taking the third electron, the fourth electron, no matter if I'm going across argon, going across chlorine, going across sulfur, there's no exceptions here. Taking the next electron, the second, then the third, then the fourth, then the fifth, until they're all gone, becomes harder because we've got a higher ratio of protons to electrons. It's like we've got a stronger and stronger and stronger magnet, or the same magnet, I guess, trying to hold less and less things. So that is an important idea there. We can remove one electron, it's harder to take the next. No matter where we find ourselves in terms of Zeph, in terms of shielding, that next one becomes significantly harder. In the next few videos, we'll look at the other exception or the other explanations of why we see some patterns here.